Yeah, we'll start now. Uh, Good evening, everyone. Um, my name is MD Asjad Raza, PMRF scholar in the Department of Mechanical Engineering, and today is the 12th week of the session. 12th week of the session for the course of a statistic for biomedical engineer. So we are on the last week of the session, and today we'll see like what are the topic that has been left out, and plus we'll try to brief from the starting to the end how it went out, and then I think your exam will be in coming week. I think in 2022, na something is there, is it?
26th, no, sir.
Yeah, 26. And the pattern is something like that will be multiple choice question will be there. I think hopefully that you got the mail.
Yes, sir. It is computer-based exam. It was there.
Yeah, yeah. And it will be multiple choice question, and one more thing like that numericals will be something called that will be not much calculative way, and if you have some friends you can ask to them like how they went that how they gave the exams and all. Okay, so the whole
But
idea
this
of this
12th,
sorry.
sir, this 12th week assignment is so different, So it's not multiple choice question. It's like a subjective form.
Yeah, it's in based on the Python. If you are familiar with the Python, then it will be good. Otherwise, when is the last date for the assignment?
The Wednesday, sir, coming Wednesday. 15th is the last date, I think.
Okay. So I think that out of 12 or 13, they will be going to consider the 10 best assignment. I think it seems so.
This is 10 questions, sir. This.
Okay. Okay. So we'll try to wind up that one, and I'll try to make some Python. Or if you are familiar with that, that will be easy. Otherwise, I'll do one thing like previous year question will be there that I'll make the PDF, and then I'll put in the and that the drive link and drive link.
Okay, sir. Okay, sir. That will be better.
Yeah, that will be better. And because if we are like family, like I'll just explain what's happening with the Python and all, like how we can do similar way, and then after we'll wind it up. Okay.
Okay, okay, sir.
If any other doubt is there.
Only this week questions alone doubt.
Okay. So we'll be having some question like similar to that one. Like I'll make sure like something because it's a Python based. If I'll start explaining that from the Anaconda and then giving the basic brief of that. So I'll suggest you to go through the whole week of the lecture. Like that the last lecture is there, na? Have you went there? And that the last
Yes,
video.
sir. That's full one. Last videos only regarding on Python.
Yeah. So if possible, so just go through that, try to get it. Otherwise, I'll make sure some concept and then I'll keep the PDF in the what you can say in the uh, that one that link. Okay.
Okay, okay. We are from medical field, so little finding difficult regarding Python.
Okay. Okay. So I think that the whole course agenda, so something like to start with the statistic and on that to with the course of for the biomedical field and all. So when we're saying like we have to go with the anything in the biomedical engineering, so that's a very critical. Like we have to discuss about the human that, and we have to take the decision for the human and by the human. So there will always chance of the error will be there. So that's why, so we have to be very careful when we are going to that test a drug or anything, that we have to, or design any equipment for that, that's a medical and all. So we have to be very careful with that. And even what we're making the interpretation, like it's something that's the play with the life and death of the, like some like populations and all, like it's a field of uh, human being and all. So it's very important. So in that itself, like we have seen that application of biostats, that is statistic, where it will going to help, that we have seen in the case of human, and we'll be having that animals will be there, or maybe if you go with the agriculture and all. So it's going to all, like we'll be having very important things to discuss, and then we have to make the decisions and all. So once we have to take decisions, and also we'll be that we should have the full background, like we should have the idea of the what about the data, and how the data we can describe, and to supporting the statistic we need the probability, and how data is distributed, that call distributed and all. So then again we have seen that what is the role of the probability also in the statistic. It's a that the foundations of the statistic actually. So just the similar way we are saying for the case of machine learning. So for the machine learning, that the foundation is that algebra, and we'll be having that statistic and probability. So that too should be the like we have the fundamental. So for the statistic, we should have the idea of whole probability. Like we have to play with the like confidence interval and then p-value, and that what you can say, like we have to make confidence level to increase or decrease, or either like power of the test, and also it's all based upon the probability itself. So that probability and all, that will tell like what are the occurrence of the chances. If we define the probability, it's something called chances of the occurrence. So, and in that we have to then that before that we have to descriptive that a statistic that need to be seen, that a descriptive means something called like that we have the mean, then median, and then mode will be there. Is it? So these all things we have seen. Then I started with the probability theory. That like we went to what we can say, something called that conditional probability and all, that we have seen, and all probability and all that we have seen, conditional probability, and then other probability that and some distributions like that how it will be going to properties of addition law, all the multiplications law and all. Then we started with the probability distributions, like how the data is distributed, or like how the probability getting distributed. Like we were having binomial distribution was there. Then we were having Poisson was there. Then we were having something called the normal distribution was there, and all it was all was there. So then we have started with the like it's this is the all based upon the something called that description. Then we came across the expectation, like it's a extension of the mean actually. It's they're going to they are going to calculate for the context or extended the mean. Then we'll came across the variance also. It was the whole things that we have seen around. After that, we have just introduced the sample that is statistic, and then inferential statistic. And that after that knowing the whole parameter regarding the probability and all, then we went to the inferential statistic. Like we have to make some decision based upon that, based on that. Okay, and like inference is something like that we are going to make some inference. Inference is something like we are going to make some conclusion. So that we were able to make based on the probability and all, like, or we have to how to make it all. So it was something called hypothesis and all. It was there. So it started with the that the central limit theorem. This is the fundamental statistic that need to be started. Like there we don't have any data normality conditions and all. That should be IID, like something called like it should be independent, should be there. And then we started with the hypothesis testing. Once we'll go into the inferential statistic, so we'll be having the hypothesis. Like we have to when we'll start something called the statistic and all. So we have to make some assumptions or some hypothesis. Like it's two types of that hypothesis we have. One was the null hypothesis, and second was like something called alternative hypothesis. And if I'll explain the that null hypothesis is something that null actually. that status quo, like something, let's say I'm going to check with the two drugs, and that two drugs having different compound, and that two drugs have a different what is the content and all. So first we'll make a status quo, like okay, there's no difference between the drug A and drug B. So that will become our the null hypothesis, and then other will become the alternative hypothesis. Like, that means there is some sort of any differences is there, that based upon the data and all that will change. And in that also we were having that alternative hypothesis also. It's like something called two-tailed test, and the second one is we're having either that one-tailed test. In the one tail we were having something called right tail. Second one was having, we were having like left tail. Like first we'll make okay, there is no difference in all. Then after we'll say okay, between the two, which one A is better, or like maybe the A is less than B. That something will make some like conclusions and all. So then after we have checked for the large sample test. For the large sample test, like it's going to be when we'll have the number n greater than 30, that will call large sample test. And then correspondingly p value we have calculated from the table also. Like once we'll calculate the f t value, like just one minute. So once we'll having that like that t what was T statistic or F statistic and all. So based upon the T with corresponding to the degree of freedom, that we can get that P like the value of probability at the particular from the table itself. So that we have calculated. Then after we came to the sample, that a small sample test, like when when we have the number of sample with less than of 30. Okay. So in that we were having T distribution test we have, like a student T distribution we called a student T test. In that we were having some 3 to 4 cases were there that we have seen already. Like first one was like when we have a pair t test, then independent pair, then like a pair t test, like then we have checked with the variances, like variances also that we have checked there also. So once we will going with the any of that null hypothesis, that we are able to tend, or we are able that the chances will be there we'll doing some mistakes and all. So based on the conversation level, so we are having two types of the error: type 1 error and type 2 error. In the statistic, type 1 error is very dangerous actually. Like something, if we are not able to reject the null hypothesis, that will become the type 1 error. Or that was the, like we are supposed to reject the null hypothesis, but we have accepted the like that not that we didn't get the value, so that become the second type of error. So we were having contingency table. We were having like it was that the right and like what you can say predicted one. So yes, no, then yes, no. So if yes, yes, so it will become the vacant here. If we are going to able to make like this here, so that will become the type 1 error. Like it was supposed to be no, but what we have done, no, it was supposed to be yes, but what we have done, no, it's no. It means like type 1 error, like we're not able to reject the null hypothesis and all. Then this will become your type 2 error. So these are the thing. Then we have checked with the power of the test. Like when we're saying like, okay, I'm going to reject the null hypothesis. Like say that we are telling like, okay, I'm going to reject the what do you say? Reject the null hypothesis. So means like what is the power? Like 80%, or what is the confidence that we have? We can tell. So that's what like that will come power of the test. Like something called interval and all. Then after we have came across the chi-square test, like it's called fitness of the test and all. Like let's say if some data is there, we're going to make some assumptions, like the data is actually following some binomial distributions, or maybe that Poisson distributions and all. So that how fit the data is there with the particular distribution, so that will comes with respect to the chi-square distributions and all. So in that case also, like it's not going to be like always, it's going to be like this, make like this. If the if the if the number of samples will become more and more, it will become the normal distribution. So chi-square distribution, like it's something, it will be like flat. It will be always positive side. It will not go negative side. Once we talk about the normal distribution, so we'll be having like this. It will make the symmetry curve. Then after hypothesis test, doing that's called using the variance. Like the idea for the statistic or maybe like to do so, it will be like always there is a difference in the average or like there is change in the average. But the way we can calculate that can be of different thing. Okay, so so that can change. So instead, first we were checking with the calculation based upon the that the mean or average, or maybe the that the differences in the mean and all. So now that will not give the clear picture. So now we have to check how much error or the variances is there from the original data. So for that we were having called F test. Okay, F test was there. That F test actually they are going to calculate the differences in the mean, like for a sample based on the variances and all. Like so that F value will be going to be that the higher variance by some sort of lower variance and all. Okay, so that was the things that we can do. And then after we were having the test of independence also, and then probability plot. Probability plot is something will be we have to check with the how data that's called QQ plot and all. That if we have like this, it will go like this. So then it will become the normal distribution. If it became like this, so it will become like that's some sort of some non that normality will comes into the pictures and all. So to check that our accuracy and all, that we have to go with the QQ plot to check with the what we have done the testing is correct or not. Okay, so then after we were having that that I told one will be the paired t-test and second will be two independent paired t-test. That test will be there and all. Then F distributions that going to use with the variance and all. Then we started with the ANOVA because that the problem with that F test or the t-test or chi-square test and all, it's something that we should have them that the maximum of two groups only. Like two groups have or two populations that we can take it out. But let's say in the reality that we'll be having three types of the that the group will be there or three variables will be there and all. So then we have to introduce the ANOVA. So in that it's actually like something called that is will discuss more about the sum of squares. Either it's called that's called mean squared in terms of the treatment or in terms of that we'll be having the sample, and we'll take the mean square error, and we'll be going to calculate the something called ANOVA table. That ANOVA table will I'll be seeing like source will be there, and we'll be having that what we can say that treatment, and then that one more sample will be there, then error will be there, and then it will go into total. Then we'll be going to calculate the SS, then degree of freedom, then MS. That MS is something called that's called mean square and all. So that is the one session we have in the coming like either it's on Tuesday actually we'll be having one session that I will give the brief for the full idea like how it will go. Then we have then after it came the covariance and correlation. Let's say now we have checked with the okay there is a differences are there like that. Then we have to fit the curve. It's linear curve or the correlation. There is that we have two things are there. One will be the covariance and then correlation. Covariance is actually the mean like we'll be having two separate things and then there how like their variance like that how that the both variable is varying each other. But if we talk about the correlation, we'll be having like something called like this how it's correlated with the one variable to the second variable. So it's something directly correlation. Covariance is something that how that variance in that two variables how it's like something that they are correlated and all. So that are two things we have. Then we have fit the simple linear regression. Then we have checked with the coefficient of determinations also r square actually coefficient of determination like r square. Then we have checked for the multiple linear regressions, then adjusted r square. Then we came across like when we are going with the normal or something called simple linear regression, so that might not give better pictures or like it's always the data will be not always the it's like highly correlated and all. So with that we have to check with the logit function or the logit function actually that LR actually used for the binary problem like either yes or no spam is there or no or either that there is the something called either zero, either one. There is no in between. But in the case of a simple linear regression, that we can go with the continuous data, like we can play with the continuous data and all. Then we have checked with the we have fit the actually what you can say that the linear regression with using the no for now that we have done for the ANOVA with using the linear regression, like we had with that we that we were having A and B was there, then we have confounded, and then from the then we came across again that we have divided into a two variable. Then we calculated the ANOVA. So now this is all things we have seen. Then in the coming week, then we have checked with the design of experiments, when the number of groups and all it will going to increase, and also then how we can do the blocking, like we'll be taking the all homogeneous the group in a place, and then we're going to make a block and all. Then in that we were having the RCBT. Before that it was CRD, like complete randomized design. Then we came across the Latin square design. Then we came about the GLST and all. So in that we can control a zero variable, but here one, like here one, then two, then here we can make the three. Here that we were having Greek letters was all were there, that we can make, that we were able to make the confounding and all. Then we introduced the factorial design. Factorial design is something called 2 to the power k. So 2 will be the label and k will be the factor. K will be the factor. And till now in this subject we are discussing more about the two factor. No, no, two label, and then 2 to the power 2 will be that will become two factor. So then after we have discussed the interactions, whenever if you go that individually, that the two things will behave different, but what will happen sometime one will be depends upon the others also. If we don't take that parameter into the picture, but what will happen with that, we are not able to give proper results, or proper inference will not able to give it. So means that we have to introduce the interactions also, because A that all alone will give one picture, B will give all alone one picture, but interaction between the but the interaction between the A and B also will have impact on the our results and all. So that is very important things that will comes in the picture. So from there only we have introduced the something called two-way ANOVA. So means that we are going to calculate the A factor alone, B factor alone, then we'll calculate the AB, then we'll calculate the error, then we'll calculate the total, then we'll calculate the ANOVA, and then we can make the decisions and all. Okay. So then after then for today agenda is actually we are going to discuss more into the factorial design, like design of experiments, that will see to the power of 3 factorial design. And before that I'll be seeing some more problem or some more discussion on the two-way ANOVA, and we'll see to the power 3 ANOVA, like we'll be having two level. That level will be two, but the three factor will be there. So in that itself we'll be having like A, B, C, what that will come individual. Then we'll go with what we can say that that AB will comes into picture, AC will comes into picture, then BC will comes into picture, then ABC it will comes into picture. That how that we can design the experiments and all, because that's the important part and all. So if you see that two-way ANOVA, actually these things we have discussed in the last class, but still will what do you say just go through that. So ANOVA is actually they're going to technique for the comparing the means of group by examining the variability in the data. Like they're going to check with the that error actually, that how much is there. Then based upon that they're going to take or they're going to give some interpretation of the data, particular data and all. So if comparing the mean group across defined by a single factor, like that's the only factor we have. So effect of different fertilizer on the crop yield. So that's the only thing, like different of the fertilizer. So in that case, that I'm not going with the soil and all. Soil I took as a dummy, but I'm checking only okay, whatever the soil type we have, or that the single soil, I'm going to check with the different fertilizer. So what is the effect of the different fertilizer? So it's will that fertilizer can be 2, 3, 4, 5, 6, but the thing soil will be same. Or if we have some soils also, that will going to make confound, and then will make one. So means that is single factor. So it means single factor itself is the fertilizer, we are not more bother on the soil. And the second case, if the second case, like we'll be having effect of the fertilizer type and irrigation method or fertilizer type plus the soil that the soil. Okay, so means so if we have both factor fertilizer type or soil or fertilizer type that irrigation or irrigation plus soil and that what is the soil one soil two and all. So means that we are taking two things together. So in the soil we can have one, two, three, and fertilizer we can have again one, two, three, and irrigation method also we can have one, two, three. So if we have a combination of one, two, or two, three, or that one, three, so means that we have to take two factors simultaneously, not three factor. If we take the three factor, so that will become the three-way ANOVA. Okay, so in the two-way ANOVA, that will be having two factors that we're going to discuss simultaneously and all. So one-way ANOVA, it's going to be like single factor, but two-way ANOVA, it's going to be like something called the to test actually to that the main effect of the factor A, then the main effect of the factor B, then we'll check with the interaction also. Till now, we were having the t-test, we were having the chi-square test, then we were having f-test, and one-way ANOVA we are having, and before that we were having the central limit theorem. In all the tests, we didn't talk about the interaction. Okay, so here it was the all factor or the groups, it was individually and then we are trying to compare directly. Compare directly means like not like directly it's plus based upon the descriptions. It was not based on descriptions like we are taking the mean. Okay, this 10 is there. That A mean and B mean 12. Okay, that we have the differences are there. No, we are going to check because the A that came from sample of 30, B that came from sample of 30, but their average is 10, but we have to check whether any significant difference is there or not, so that we can check through that the number of sample they have from 30, so we can go for the t-test or chi-square test or central limit theorem. Then we can make, okay, if the p-value is going to come less than that of 0.05, so we can say, okay, that so there is a significant difference is there, because we are not going to tell the based on the description, because we have to make the decision based upon the that statistic. So means that we have to check with that some t-test or we have to calculate the error and all. So then we'll say anyway by seeing the number, by seeing the that 30, that the 12 and tell there is a difference is there, but the thing whether any significant difference for the average and all it is there or for the whole populations and all. So that we are going to make. So here it was we have calculated all uh, individual for the factor A also, for the factor B also, that we took the individual. So, but the thing in the reality or in the that application part and all, that will be that let's say I have let's say I'm going to say the soil one, two, three. If we have the fertilizer one, two, three. So if we take individual soil, individual fertilizer, that we can get the results. But the thing is that soil one and fertilizer one, it will make some other difference. Soil one, fertilizer two will make some other difference. So means it's the interaction is there. Means like one is actually depends upon the other factor. So that is something that we have to introduce or we have to tell. So means that we have to tell like in a so that's why like we have to make sure like that the interaction like it's something called common. That's called union. We have the one individual. Second also their union. So this is the interaction that's coming. So if we are going to neglect that one, what will happen? That we are taking one. Then if we are taking so the chances of the overfitting will happen. Overfitting or maybe the underfitting sometime also because of the based on the data and all. So actually this concept will come into the more into the machine learning. When we're going to fit any of the curve, maybe that we have seen the simple linear regressions and all. So it will comes into the pictures and all. So that's why it is very important to that we have to see in our. Okay. So if we talk like some based upon the that so two-way ANOVA analysis method to study a quantitative for two or more category explanatory variables and all. So then that if you see the Assumptions will be the always that we have seen, that independence of the data should be there, that each of observation is independent of the others. So ensured that we have the taken the proper something called the randomization of the, it's a part of design of experiments. That the randomization design of, so actually it's a part, something like we have to design the properly. It means that we have to do the randomization and all. So that will make sure that our data is independent of the each other. Then we have to make sure that in the normality test, like that our data should be, or the error, that the variance should be, that should have the, what we can say, that that should be normally distributed. Like data should be normally distributed like this, mu is equal to 0 and all, like should come. Then that we can check through the QQ plot that I told, that the probability plot we are, or either Shapiro Wilk test is there and all that, check with them. Then homogeneity of the variance means that if we have the one group, two group, three group, so that the variances are equal across the all group. For the case of the study, I'm saying, let's say I want to do the study for the EMG, that I have a two group. That the two that the two groups are the, one is trained and second one is the untrained. So in the trend, what I'm going to ask to make sure that they're going to lift some load, lift 20 kg. We'll be having some dynamometer is there and all. Second case also we have asked to load the 20 kg and all. If that load value we are going to take or lift the weight, so there differences in the variances for the group. It should come like, let's say I'm going to say no, it should be less than 5%. So means for the both group, it should be less than 5% only. It can't be this can be 7% or 6%. So means what will happen? They're going to lose the that assumptions, means it's going to violate the assumptions of the, what you can say, uh, that is the two-way ANOVA and all. Then additive, like, so there will be no directly additive and all. A and B, no. It will be A B, like its interactions and all. So means it's not going to add the linearly and all. And then it interaction included, we explicitly model A B, not the A plus B or A minus B or something. So it means something they're going to make some differences and all. So this is the whole thing that we have to think about when we're going for the any testing and all. So this is the all something called parametric test and all. But sometime what will happen? The data will be the not normal. Is it? Like data will be not normal, or the data will not follow that this assumptions and all. Then we have to go for the non-parametric test. If we have a two groups, so it's called moon whitening test and all. Like we have the different testings is there that we can discuss in that, like that if you go into the that the machine learning part, that we can see more into that. So actually this whole test is actually based upon the parametric test. Like it's that something we have to assume that our data is going to be normally distributed and all, and that we are making that assumptions also, like that the variances are equal across the all groups and all. Okay, so if you see some example, I think this also we have seen. So I'll just explain that how it will go. So that what they will do, the researchers and all, they will go to examine the effect of the two treatment simultaneously, where both treatment have the nominal level of the measurements. Like it's something that we have some six, that the significant measurement will be there. Let's say I'm going to make some the same thing EMG, that's called electromyography, and will tell with the load that we came across some sort of muscle activation. Okay, so means that muscle activation is actually going to depends upon the load. So that we have to see out. Okay, that we need to see out. That if we don't see and all, so means that we have to check with the simultaneously. So in that also now for this study we can have different groups that will be there. Maybe for the age category, 15 to 21 batch, or 20 to 25 one batch, or second can be trained and untrained, and a third can be some other group, like it's either male or female. So it's something that will be having some two factor we can deal simultaneously involved. So in that also, if you see the some sort of examples, That effect of the male and female on the races on the wedge. And race means something called region, like white, or maybe the African, or maybe the Asian, or maybe in that Western and all that it was see out and all. Then we can check with the effect of the level of that the pollutions and the level of the city services on the housing prices. Okay, that we can also check it out, and then that we can do it. And that again we the check with the religion, and then region on that the income also. See, something like we'll be having some that example can be of anything. Let's say for that for the region of Europe, and for the region of this that Africa, or maybe with the Asia, that FDR, that particular something called a drug regulatory, federal drug regulatory, like for them it's different. For the case of Europe, it's a different. For the Russian, it's a different. For the Asian, that we have difference and all. Why? Because that the genetics is different. So that thing we have to check it out when we're going to do any study and all. They will do the testing and all. But they have to check with the diversity and also. But if they have come up with some sort of drugs and all, whether that significant, that effectiveness of that drugs, actually they have to take the sample from the all over the country, and then based on that they have to make some decision, or they have to tell, okay, my drug for that particular diseases, it's having 70% effectiveness is there, or 60%, or that the 70%. That the same thing happened when the COVID came. So first of all, the Covishield, then what is it, Covaxin. Then it came to that's called booster. Then that one some call Russian and all that from that Russian federal, that the federal, that what you say federal it came. That forgot that the name of that what you say vaccine. Okay, so means that we have to take care all the parameter, whatever the variability will comes into the picture. And when we are going to take variability, one thing that we have to make sure it should not have more and more confounding. Like some factor will take, but it that doesn't have that much impact on that. So that we have to reduce it also. That's what that the concept of the RCBD came, and then see that the CRD and all came. So if we are not going to eliminate nuisance factor and all. So there might be chances that again, whatever the interpretation will come, it might not helpful for us, or maybe that is not correct, and it will impact our whole study, or that the whole direction, or even that because it's called biomedical, and then people that's going to for the animals or the humans or any other thing that will, but it will affect. So we have to be that very careful in all. So if you see the two-way ANOVA, it's something called the classical experiments and all. So that what you have to do, it's going to we have to start with that, like how it will go. Let's say that primary focus is the balance design. Balance design, something called like the group one. It's have 30, so group two will be having also 30. If it is 27 or 28, it's called imbalance design, and it might impact our thing. So that before proceeding for the test and all, or before proceeding for the anything, that we have to take care of this parameter, that we have to specifically design. Okay, for the group A, that we have some only 25 people, or for group A, that the group B only we have the 7 people and all. So that need to be taken care. Yeah, otherwise, due to the imbalance, it will become the favor of the A or favor of the B. It's something like it's become like bias results will come, or maybe the overfitting if we are going with the fit curve and all. So we have to take care. So that's why if there would be a five white males, so five black males also, five white females also, five black males, it means everything that should have the quite common. Balance there unlikely in survey research, but because in the real time, like if you go with the participants for the EMG study or any biomedical studies and all, sometime for any study that we'll design will take 15 male and 15 female. But what will happen once the experiment got finished? Maybe we'll able to came up with the 12 male and then somewhere 10 female only. So means there is an imbalance came. So that thing, but that need to be taken care. So So that need to be like we have to properly design or properly do the testings and all. So again, I told you like to deal with this all these problems and all. If you go with the manually and all, it will be very typical, or it's going to traditional method. It will take too much time and all because we have to calculate the some of the total squares, then some of the that is called main effect and all. So it will take much time. So now we have the SPSS software is there. One, either if you have the bit good in the MATLAB code, that MATLAB also can be there. Or if you are in good in the what you can say something called uh, the Python. So Python will help you out and all. And for the this week actually we were having Python things and all. I'll just make sure like it will come because I'll just show like how it went and all because I have seen through the lecture. And if not possible, then I'll make a fundamental PDF and then I'll put in the groups and all. So if you see that how we were that handle in the last case, like that yijk, that's going to be output function, output and all, and that's called mu plus alpha I bj plus alpha beta. So that the alpha I will be the effect of factor A, and that the mu will be the something called grand mean or the total mean and all. Then beta j will be the effect of the factor B, because in the ANOVA we are having only two factor, two way ANOVA, two factor. If it is one way ANOVA, only one factor we have. So so first we have taken for the something called main effect of A, then we were having the that's called main effect of B. Just because that we are going to the two-way ANOVA, so we'll be having the interactions also will be there. Interactions will be also there. So then we have that we have to go with the alpha beta ij, and that we can't take like let's say we were having the assumptions, so that we can't take the alpha plus beta. No, we can't take because it will be always it's going to be interaction like something called multiplications and all. Then this is the error or something called residual. So this is actually a what do you say model for two-way ANOVA. So in that also like then we have calculated the something called ANOVA table. ANOVA table will be factor A, factor B, then interaction of A, B, then error, then total of B. Then after that F, we can calculate like from the MS of the factor A, factor B, or the interactions by error. And that the error will be the always denominator and all. But other thing we can check it out. And the degree of freedom for the factor A, for the factor A, like that fact for the factor A, we have the some 3 to 4 values. So A that's called A minus 1, then B minus 1. For interactions, that will come so A minus 1 into B minus 1, and then AB into edit, that is called N minus 1 for the error. And if you go with the total, if you go to AB N minus 1. So it's something like if you go with the full derivations, and all that you can see out and all like how that we can calculate and all. Why we are going with that 1 to 1 and all, because it's 1 is actually we are calculate the mean, so that should be uh, like that should be subtracted and all. So then after that how we'll calculate actually SSA. Let's say if you go with the this is called going the that's called row side and then column side, so it's called B into N. SSA. So 1 by B into N. A, so B, and then number of sample, and summation of TI square minus GT square. GT called something called grand total. That we can calculate and all. SSB will become 1 by AN, summation of TJ square. It's let's say this is the I1, I2, I3, and this is called J1, J2, J3. So this summation square, Tj square, by 1 by An. N, how much number in this? And A will be something called this, that number and all. So similarly for the SSAB, it will be 1 by N, Tij minus SSA minus SSB minus GT square by N. It's a Tij square actually. So it can go, and then we can calculate and all. So once we calculate the SST, SSB, SSA and all, so we can calculate the SSE. SSE is called sum of squared error. It's called SST minus SSA, SSB, and SSAB. So this is actual effect, actual main effect of A, main effect of B, then this is called interaction. So once you have done with this all things like calculation and all, so that we can calculate, we can create the ANOVA table, then we can make based upon the F value with corresponding to the degree of freedom. That's why whenever we talk about the ANOVA, we have to correspondingly we have to talk about the degree of freedom. For this degree of freedom, for this degree of freedom, for this value like F value, like that the P value came. So based on that, we can either we have to reject the null hypothesis, or either we have to say we don't have enough evidence to reject the null hypothesis. Because in a statistician and all, statistic and all that we have to tell, we can't say like we are going to accept the null hypothesis. We'll say we don't have enough evidence, like has something to play with the diplomatically and all. So if you see the examples and all, so I told you like that we were having the fertilizer type. We have the A, and then irrigation, like for A fertilizer it went to low, then it went to the medium, then high, then B also, then it went, then their yield came. So first we have to calculate the that's called a GT. GT called grand total. Grand total 50 plus 52 plus 55 plus 54 plus 58, 57, 53, 54, 56, 55, 60 plus 59. So that will come something called 659 and all. Okay. When we have calculated the what is the total number? We have that 1, 2, 3, 4, 5, 6, and 6 yield in that called yield 1, then yield 2. So total become n is equal to 12. Then we calculate the SST, sum of total. Summation of square of summation of square of whole the sample minus GT square by n. So it will 50 square plus 52 square plus 55 plus 54 square till 59. That then minus of 659 square by 12. So we can calculate. Then it came the that SST. So now we have the idea to calculate the what SSA, like itself, because if we go with the that ANOVA table, we are having factor A, factor B. Factor A is something called like it will be the factor A, then factor B. Then in that factor that we have the levels are there. In factor A, factor B, then this is called level. So when we calculate the for a fertilizer A, and so if you calculate the FA for fertilizer A, it will go 50 plus 52 plus 55, 54, 58, 57. So it will calculate the 326 FB. So we can go for the fifth, that called 53, 54, 56 and all. Then we can go for fertilizer FB. Then it came factor B for the TL. That means called like TL, like treatment or irrigation low, medium, high for the factor A, for factor B. So for low with that will be having 50, 52, then it will come 53, 50, that the 54. So we can calculate 209. For TM, that's the 55, 55, 54. Then the medium we have 56, 55. So it will come like this. So SSB will become 1 by B into N. B something we have how much? 2 and 3. No, 3 is the number. B will be the like something called how much that how many numbers we have. Then we calculate the SSA. Then SSB we calculate similar formula 1 by 2 into 2, and the summation of the TJ square, all things will come into picture, minus 629 square by 12. So that we can get it out. So once you calculate the SSA, SSB, now that the idea is to calculate the what interaction. For A, we have the low, how much? For A, that the medium we have. For A, that the high we have. For B low, B medium, B high. So now we can calculate the SSI 1 by n. So it will become 1 by 2. And then 1 by 1 or 2 square plus 1 or 9 square plus all will go till here minus SSB minus GTU square by n. So once you calculate what we can say that SSAB, that we can, so we can, that then we can calculate the degree of freedom for A, 2 because of fertilizer A, fertilizer B, 2 minus 1. For the B, that we have irrigation method that's called low, high, medium. So we can calculate the 3 minus 1 into 2. Then that AB also like interactions, then error, then total. So we can make here factor A, factor B, AB, error, and all. Then after we can calculate the what we can say F. So MS of A, MSE, or MS of B by MSE, or MS of AB by MSE. So something it will come like this. Okay. So then after, once you got these values of F at degree of freedom of like something will call come 6, 11. We go to table, we'll see 6, 11, and then we'll be able to calculate and all. So this is how that our things. Then if you calculate the R square, SSA plus SSB plus SSAB by SST and all. So this is the whole idea of what you can say something two-way ANOVA. I think this part is clear. Na? Two-way ANOVA is clear, na? Or any doubt is there?
It's clear, sir. Doing
So this is clear actually. Then we can go. And now I'll introduce something called factorial design. Is it? That will be okay, na? So factorial that the design we have seen, like we'll be having a number of factor will be there, and fixed number of factor or fixed number of that level will be there. Just 1 minute. Will be there. So that we have to see like that the that in the experiments that involve the study of the effect of the two or more factor. Once we were having one factor, so that we were dealing with the one way ANOVA, that we don't have to go with the any of that heavy weight method. We went to the something called lightweight method, like we were having t-test or either a chi-square test or something that we can go through that. So in general, factorial design are most efficient for this type of experiments when the number of factor and all things will increase. So it's better to have like factorial design. It's like something if we have 2 to the power 2, so it become 4. Like we'll that we should have the sample. What do you say? 4. That number of things that should come 3. 2 to the power 3, it become 8. 2 to the power 4, 16. So means it's called replications and all. If we have a 3 by 2, it's a 3 factorial design. Like not 3 factorial design. 3 factorial design will come into the picture and all. So that's why we have to properly designed. We have to make sure arrangement should be proper. Otherwise, it will be very difficult to handle with that. By a factorial design, we mean that each complete trial or replicate of the experiment, all possible combinations of the level factor are investigated. We'll be having high, low, no, low, high. Again, we have the low, high, factor A, factor B. It will come like this. And this we can calculate, and also that we have to take this will come one that I'll tell that how it will come and all. Then after so it means possible all possible combinations A, AB, B. If we have three A, B, C, AB, BC, AC, again ABC. We have the four, we'll go with the A, B, C, D, AB, BC, CD, then ABC, then it will go the ABCD and all. Like it's all four possible way. Like it's called that's called permutations and combinations and all. For example, if there are that level of the factor A, B, level of factor B, each replicate contains all AB treatment combination. It's called interaction. Okay. So when factors are arranged in a factorial design, they are often said to be the crossed. So it will be interaction like this or interact like this. Either like this or either like this. I'll show you like how it will look like and all. So that we have seen also that how to calculate actually what you can say, that effect or the that's called main effect of A. So it's something like that is the average of high minus average of low that we have done here. Factor of B, like for factor of B, that's called x plus y by 2 minus z plus t by 2. That we can do like here this way. This no x plus y and here if we have the y plus 2 y plus t by 2 plus x plus z by 2. So it's and if we have to calculate something called interaction, so that we have to go through the like this y plus z by 2 minus x plus t by 2. So means interaction will comes crossed like how it came. It means like this one with the two like two, three, four. So one with the three, two with the four and all. So this is the actually important part. So then after we that we have the sub value was there. So if there's no interactions, how the line will look like? It will be like this. If we have the interaction, one will like this, one second can like this. So something like we'll have some common grounds will be there. So we have done calculation also here. And if we have something like at the level of A, at the level of B, then we can calculate that interactions also. How we calculate 12 plus 20 by 2 minus 50 plus 14 by 2. Then we calculate here and it came. So if you see that if we have there is no interactions, it will come parallel. It will going to be a never ending meet. If we have some interactions, it will be always something will come that x something there it will cut and all. So this is a similar case of that what you can say actually 2 by 2 ANOVA like 2 by 2 actually something called two-way ANOVA only actually. So if you see that the similar way we have checked for the two-way ANOVA yijk mu plus alpha I beta j plus alpha beta ij plus error. So here if we going to fit the regression line, so it's a beta 1 plus beta 1 x1, beta 2 x2, beta 1 2 x1 x2 plus error will be there. Okay, so this is how we have to regression for the two factorial experiment that can be written. That we have discussed also like that how we'll calculate and all that we have to that we have figured it out already. If you see what is the advantage of the factorials, so it that is going to make easy for to conduct the experiments and all. That the let's say that the advantage of the factorial design that we can see easily illustrated. Suppose we have a two factor A and B at each at two level. It's a high. It's called low and high, low and high. This is called low, high, low, high. So we do note that the level of the factor by A minus 1 means A low, then A high, B low, B high. Information on the both factor could be obtained by the varying factor on a time as shown in the figure. If you see here, like here, the effect of the changing factor A given by A plus B minus 1. If we go at one point, either minus of A minus B minus 1. And the effect of the changing factor, it can come A minus B plus. Like I told you how it will go here, cross. And then minus of A minus B minus. Because the experimental error is going to present, it is the result to take the two observation, say at each treatment combination and effect factor is going to respond. So total of 6 observations that we have to require now. Okay, because A B N minus N. We had that so that's how it came the total degree of freedoms and all. So if we check about like how we can calculate and all, so that the similar way it will go that the two-way ANOVA. We have calculated the A treatment, B treatment, interactions, error, and total. A minus 1, B minus 1, A minus 1 into B minus 1. Then we key that for the error we have calculated also here, then here. And then how we have calculated also that we have also checked it out in the two-way ANOVA. Is it? So this part actually I'll keep it again. So now we'll go with the will start with a 2 to the power k experiments, like a 2 to the power k means that the level will be 2. Now number of factor will change. Factor will change k. So if we have the important case, special cases is there that the k factor each at only two level. Let's say B high low, or maybe shop light heavy, or if it is fertilizer, maybe the fertilizer A, fertilizer B, only things can go. So that we can have two levels, but the factor will be different can be there. So this level may be quantitative. This level such as two value of temperature, pressure, or time. So in the temperature, number of sample can be anything, 10, 20, 50, whatever. For the pressure, time. So they may be the qualitative, such as two machines, two operator, the high and low level of the factor. For a machine to operator, it can high and low level. But in that also we can have the factor temperature, pressure, time. Means level will be two, but the factor can be anything. If we have the two factors, so that will become a two factorial design. If we become three factors, so that will become to the power like two something called two level three factor design, two level four factor design and all. That's how it will increase. So if we are having something called k factor, so a complete complete replicate of the such a design requires a 2 to the power k observations. So that's why we have to very careful with that. So that's why we call 2 to the power k factorial design. So 2 to the power k design is a particularly useful in the early stage of the experiment work when many factors are likely to be investigated. It provides the simple number of runs which k factor can be studied in a complete factorial design. Consequently, so these designs are widely used in the factor screening experiments and all. So if we have the idea and all like factors, so that we can smallest number, like if we have two factor, so we can at least that we need to run four type of experiments, like four number of experiments. If we have two or three factor, it can go eight number of experiments and all. So it means we have to screen. We are doing like how much the number actually that will come across and all. So if you see that the 2 to the power 2 design, is it 2 to the power 2 design we have. So in the first design of the 2K series, it's a 1 with the only two factor, say A and B. So that's going to run at the 2 level. Like let's say it's a 2 to the power 2 means we'll be having 2 level, 2 factors. 2 levels will be having a 2 factor. Is it? So in that case, that the level of the factor may be arbitrarily, we can take low and high as an example. Consider that investigation that we can see that concentration effect of the reactant concentration and the amount of the catalyst we have. So what we have, low and high two factor, like a two level, low and high, like we have the two levels, but the like it thing can go. Then after that, the objective of experiment was to determine if adjustment to the either of these two factors would increase the yield. Means yield that we were having one fertilizer A, fertilizer B for the three different types of something called uh, that the irrigation methods was there. Then we came across the two types of the yield came. It's called replicate here. Replicate 1, 2, replicate 3. For A low, for B low, that the first time it came 28, 25 to 27. For A high means that the reactant concentration is high, but B low, 1 pound. It came 36, 32, 32. Means that we have done three times of the experiments. Three times experiment we have done. Something that's called replicate. Then, when the case of A is at the low, B at high, this case, it will go like this. So, how that the things will go and change. So, in that case, what we have to do, like we have to then so that the catalyst is the factor B, which is high level denoting use the pound 2 and low level pound 1. The experiment is replicated 3 times, means 12 runs. If we go with a replicate, if you go with a two that's called replicate, 2, 1, 2, 3, 4, 5, 6, 7, 8. Now we have the 4 more because it's a 3 replicate game. Okay? So means 2 into 2 into 3. So means 4 into 3, 12 sample. If we have 2 into 2, we have taken 2 replicate. So 2 into 2 into 2. So it means 8 replicate. If we have 2 to the power 3 design, so if we take the 1 replicate, it will come 8 into 1. If we take 2 to the power 3, 2 replicate, 8 into 2, we need to 16 experiment need to be done. Is it? It's clear or some confusion is there?
Some confusions. The replication,
Sorry?
regarding that replication allowance, can you explain?
Replication now.
Ah, yeah.
Yeah. So let's say I have 2 to the power 2 design. We'll be having the total possible cases, possible combination can be how much? It's 4, is it? If we do all possible
Yes,
cases
sir.
in one trial, so means it will come the 4 number of experiments, is it? If it take all
Yes, yes, sir.
possible 4 combination in a 2 trial, first trial we took, second trial we took, so it came total 8 number of experiment. If we do with the 3 trial, it will become 12 number of experiment. So that trial itself is called something we have to replicate. Like it's a trial 1 because let's say in the biomedical case, so we have to take the 2 or 3 trials, or if we take for any cases that experiment that we need to do the for cross checking, we have to do the 2 times or 3 times. Is it? So that 2 or 3 times called replication. Like we that we're going to repeat the experiments. I think it's clear, na?
Ah, yes, sir. Now clear.
So means like if we go with the only one time I'll do all possible combination. That's called uh, low and low. It came one. Again, same setup. Everything is same. Only we are going to replicate it again. Like let's say that I am the participants for my study, and I want to take that load should be taken for the EMG data, and I'll start the trial. So what I will do? So that I need to take the we have the 4 possible combination either with the something called low low or low high or high low and all. So we have the 4 possible combination. So first I'll start with the first trial. First trial I'll check it out so that I have to do the 4 number of experiments. Now I'll see the data is and all, or to cross check whether the data is correct or not, I'll take again replications. It's something called repetitions. So that replications that is nothing called repetitions. I think it's clear.
Yeah, clear, sir.
Yeah. So now in the case of like that, we have something like a 4 treatment combination in the design that we have. So by convention, so whenever we have that we're going to denote effect of the factor by a capital Latin that's called letter. A is going to refers to the factor A. B is going to that's going to refers to the factor B, and AB is called interactions. So in 2 to the power 2 design, when low and high levels are denoted by minus and plus respectively. So thus on the A axis it's called low level, and then that will become the high levels and all. So I think this part is clear now. So I'll take one or two page.
Yes.
I'll take one or two page, like how one and things will come in the pictures and all. Uh, and that what we were having. I'll just take this picture actually. What we were having, low, high. Okay. So in that case, A is going to represent the A is going to represent the like A high, combination of A high and B low. Means this will called as A and B represent the A at low, B at high. B is going to represent the A at low, B at high. Means this part. Okay. And AB both at high level. This is called AB. And one that in bracket will win at both low level. So in any of the design experiment, so this convention that we will use now. One A B B everywhere, anywhere. If it is all the factor at the low level, like A low, B low, it will connect that the convention as a one. If it is A and then A will be the A high, but B low. B will be the A low but B high, and then interaction will be the AB. So it will come. If it see the interactions, it will go like this. Okay, so that's it called. So this is the convention that we are going to use it out everywhere. Okay, so now that the effect of A that we can calculate, is it effect of A at low level of B? How will you calculate? A minus it will go. It's say for let's say we were having for A, how many number of experiments was there? 36 plus 32 plus 32. So it's a 3. So, so now we'll say n. We don't know that number. For this also, so A. So that A, whatever it will come summation of all. Summation of all number of trials that came minus 1. That's also, so that's how that will go. So that we can calculate. So now effect of effect of A at high level of B. How we can do it? effect of A, effect of A at high level of B, AB minus B by N. Is it correct? Hmm? So now if you're going to calculate the average effect of A or main effect of A, that we have done at this level, now we have to take the average. So A will become 1 by 2n. Why? Because it's a n is a common, and then the average, because that we have 2, so it will become like this. So AB minus B, is it? Plus, or either that the one way we have calculated now, that's how we'll calculate here. I'll show you how we have done here. Here we have done now x plus, for the factor of A, y plus t. This y plus t, y plus t by 2 minus x plus z by 2. Similar way we can do it here also. I'll show you. If you have doubt, just please ask. So it will become 1 by 2n ab plus a minus b minus 1. Either one more way we have done, ab plus a by 2n minus b plus 1 by 2n. If we simplify, it will come same results. I think it's clear now. Or you have some doubt, please ask. Is it clear? Or so similarly for B, we'll see for a B at low level of A, for a B that the high level of A, that we can see it out here. So we can, so that we can calculate, it will come B will become AB plus B by 2n minus A plus 1 by 2n. We are having AB plus B for a factor B, AB plus B by 2n, AB plus B by 2n, and A plus 1 by 2. So if we simplify it, it will come 1 by 2n AB plus B minus A minus 1. If you see the some sort of some similarity, if we have the A, so AB plus A, and then other will be the minus. For B, AB plus B minus A and minus. So this is the main effect of B. So now we'll calculate what? Now we'll calculate AB. How will calculate the AB? Can you please tell? AB, I'll take one that one more page. Just one. Because if you see for AB, it's a cross. Okay. So it can go AB plus 1 by 2n minus A plus B by 2n. If we simplify, it will come 1 by 2n AB plus 1 minus A minus B. This is the AB. It came. I think it's clear. So let's say that we'll take that example only, that we have the example here. That we have the example here. What is the value of A1, A, AB 60? So if you go with the, I'll take one minute. It was total was how much? 100, and we were having the value 36, 32, 32, and this was total was 80. The value was 28, 25, 27. AB, it was total was 90. If you see 31 plus 20 plus no 20, 30 plus 29. If you B is equal to 60, if you see the value was 18 plus 19 plus 23. So now we'll able to calculate the, now we'll calculate. Let's see, we'll take that example. A, what is the formula? 1 by 2n AB plus A minus B minus 1. So 1 by 2 into 3. AB, how much we have? 90. Plus A, 100. Minus B, how much we have? 60. Minus 1, 80. If we calculate 1 by 6, 190 plus 40, 50 by 6, it will come somewhere 8.33. Is it? Are you able to get it, or either still doubt is there? Can you please tell me? Hello? 150, 180 minus 30 minus 5. Then AB 1 by 6, AB 90 plus 80 minus 60 minus 100, 20, 10 by 6, 1 by 6.7. Okay, so now we have to calculate the what? SSA, then SSB, then we'll go to the SSAB, then we'll go to the normal way. Shall we do it? Oh, sorry, that went. Is it audible now? Hello?
What happened, sir?
Yeah, sorry, that time I think current went, that time my Wi-Fi went, so I was not aware
Okay.
of that.
Because in between I was not able to hear also anything.
Okay, okay, that thing I will do, I'll explain again. Is okay now?
Okay, sir.
So actually, what I was trying to do, I think this part is clear, na, that average effect of A, or that the main
This
effect of A.
page, up to this page, I was not able to hear, sir.
Okay, okay. So for the AB, like for the interaction, So it's a AB. It's for the case of A. For the case of A, AB plus A by 2n. Whatever the number of sample was there, AB plus 2 by, so it was something called AB plus A by 2n minus of B minus 1. B minus 1 by 2n. So I think it's clear na? This part. Like for effect of A, it will go at the high level of at A, this part AB plus A by 2n minus of B plus 1 by 2n. Is it?
Yes,
For,
that graphic is clear.
yeah. And for the B factor, it will go AB plus B by 2, AB plus B by 2 minus A plus 1 by 2n. So that is same thing I wrote here. AB plus B by 2n plus AB plus B by 2n minus A plus 1 by 2n. I think it's clear.
Yes, sir.
And for interaction, because that we told it that will become the cross. So
Yeah.
AB plus 1, AB plus 1 by 2n minus A plus B by 2n. Is it?
Yeah, yes, sir.
So now, let's say if we take that similar example only that we have for the each cases, we were having that what you can say A, so that will come 36 plus 32. It came 68 plus 32. It became total of 100 for the A, B similar, B similar, A similar. So now we are going to calculate the factor A, factor B, and then AB. So we'll use that formula only. So for factor A, it became 1 by 2n AB plus A. If we have the factor A, AB plus A minus B minus 1. So 1 by 2, 3 into that call that we have the 90 plus 100. It came 8.33. Similarly for the B, AB plus B. Just see A plus A, B plus B. If you have the AB plus 1. So it changed. So it's called minus A and B. If we put the some value, it came 1.6 and all it came. So till here it's clear now.
Yeah, clear, sir.
So now we'll go to the what is something called SS. This is the effect. So now we have to calculate the sum of squares. Next part. So we'll take 1 or 2 page and then we'll do it. I'm just giving a brief idea. Actually, this is that's not done on the something called manual base. Okay. So now we'll go with the sum of a square that is done by contrast. Contrast actually is nothing for a contrast of A. It will become AB plus A minus B minus of 1. That's all. So this is called contrast. We don't have to go for the averaging and all and the that number and all like that we have to do it, but that will not like this. So for SSA, it will become AB plus A minus B minus 1 to the whole square by 4n. For SSB will become AB plus B minus A minus square by 4n. SSAB will become AB plus 1 minus A minus B whole square by 4n. So I think it's clear. So now we are able to calculate the SSA, SSB, SSAB. So what will be the that's going to be a next step to calculate the SST. Is it? SST will be similar way that what we have done, summation of all that the data sample GT square by n. Is it? SSC will become SST minus SSA minus SSB minus of SSAB. So now we'll calculate the what? SSA. SSA, what we have, formula AB will be the value we have uh, something called 90. Then what we have, plus A minus B minus 1. So plus A, 90 plus 100, 190 minus 60 minus 80. So 60, 80, 140 plus that is total we have 190. So that will become 190 minus 150, 140. It will become how much? 50 square by 4 into 3. It's clear or not?
Clear, sir.
That SSB we have AB plus B. SSB will be plus B. 90, 60, how much came? 150. And this is called 180. So that became of minus 30 by 12. It came somewhere around 75. Now SSAB will be having AB plus 1. AB 90 plus 80, 170, 170 minus 160. It came 10. 10 square by 12, it came somewhere around 8.33. So now we are able to calculate the SSA, SSB, SSAB. Now we'll go with the SST. So SST, so that the similar way if we calculate SST, it will come summation of all, whatever the where the value we have, 18 square plus 19 square plus 23 square and all it will go. 18 square, 29 square, all that will go like this. And then minus summation of all the value square by n. So this value actually we have how much? 323. So now we'll able to calculate the SSC, SST minus SSA, SSB minus of SSAB. So now we can do the ANOVA table. Is it? Source, SS,
Degree of freedom.
degree of freedom, MS, then we can go with the F. Source we have a factor A,
SSA, A,
factor B, then interaction, AB, then error, then we have the total. So that value we got 323. No, sorry. Factor A, how much we got? 208.3. Factor B got 75.3, 8.33. Error came 3.34, 323. Degree of freedom will be, it's called A minus 1. How much we have? 2 minus 1. It will become 1. 1. This also be, that will become 1. Then 4 into n minus 1. So it came how much? 3 number is there. So it will become 8 and it will become 4n minus 1. 4 into 3 into, so it will become 11. I think this part will be clear because for factor A we have the 2 A minus 1, 2 minus 1. Factor B, that's called B minus 1. In that also we have 2. It's called low and high. Is it? Then error will become 4 number of experiment, that 4 number of possible way we have. Then we have that we have taken 3 times. So 4 into n minus 1, it will become 8. Then total number will become 4 into n. 4 into 4 is the possible combination, n is the number of trials or number of replications we have done. Then it came. So I think it's clear.
yeah, yes, sir.
So 28.33, 75, 8.33, 31.34 by 8, it came, how much it will come? 3 point something will come. So anyway, we don't have to calculate this one. If we can calculate this here. Similarly here. So I think 2 to the power 2 factorial division is complete, is it? So in that case, what we have to do, if you go with the contrast coefficient, so we'll be having effect A, B, A, B. It's called 1, A, B. It's a minus 1. It will become plus. It will become minus 1, plus 1, minus 1. Okay, I'll take one page actually. It become messy here. Just 1 minute. If you go with the contrast coefficient, so it's called effect. One possible case, B, A, B. It's A, B, A, B. So minus will become plus. Plus minus will become minus. Minus plus will become what? Minus. Then plus will become minus. So it's a similar way what we have shown it here. Here. Minus will become minus. Then so this is how it will go. Okay. So now we'll go with the 2 to the power 3 design. Means we'll be having 2 level but 3 factor. I'll just okay. So in that, suppose that we have the 3 factor A, B, and C. Earlier it was only A and B only, not 3. And the two label are of interest. That the design called 2 to the power 3 factorial design. So in that case, if you see, we have the 2 to the power 3. It will go, how many will go? 2 into 2 into 2. 8 run will go. 1, 2, 3, 4, 5, 6, 7, 8. So 1 minus. So this is the possible case that that the one can have minus 2 plus minus plus minus plus, like it's a like all possible combination. It can go 8 possible combination can go, is it? So if you see here, factor A that we have here, factor B it's here, factor C is here. So this will become A. Factor A at high, but factor B at low. Factor C also low. But 1 is actually on the all cases low. This also low, this also low, and this also low. Then we have AB. It's a interaction. Then we have the BC. Then we have the ABC. ABC will be the all high. ABC will be the all high only. So this is called B. This is called C. So that's how I'll show to you. Like it's a degree of freedom will become total of 8. So what about that main factor of A? Can you tell? Just guess it how it will be there. Main factor of A at when effect of A when B and C are at low level. When we have to calculate the factor of A when A and B and C are at the low level. So means A minus 1 will become N. Like this, it will be there, na? A, factor of A I want to find out, but all at the low level only. So it's a this also low for the factor B, for factor C also this is also low. So it will become A minus 1 by N. That N will be the number of something called replication. Then what we have? Effect of A, effect of A when B at high but C low. That is the one possible case, is it? B at high, C at low. B at high. B at high is AB, is it? And C at low, it become C. C at low, so it become this case minus B by N, is it? So now effect of A only, but B is low and C it high. What can be possible way? B at low. B at low. At what way will be there? AC. B at low. This one. AC minus C at high. C by N. So this is three possible case can be there, na? Is it? For A. For A. So this is the three possible case can be there. No, one more case can be there because when the both are low level, when one is high, one low, one is low, one high, then fourth can be when both are at high level. Is it?
Yes, sir.
So it will be when the both are at high level, it's A, B, C and B, C by N. So now to calculate the main effect of A, so that we have to do the average of all. Is it? This one individual, second individual, third individual. Now do the averaging of all four. So how it will come? If we simplify and all, it will come like 1 by 4 into n. Then A minus 1, first case, we have the AB minus B. Then third case was AC minus C. Then fourth case AB minus ABC minus BC. If you simplify this one, so that you can get it like similar way, you can get for the B also, is it? You'll get it or
Yeah,
not?
yes, sir.
And similarly, you can get for the A, B, C also. I'll tell you how you'll get it. You can see here. For the considering the effect of main effect, consider the estimating the main effect of A when B and C are at the low level. Is it? So it's A minus 1. We have done the simplification. Either way, one more way that we have done earlier cases, like it was like something called, so it was like something A plus B, like 1 by 4n, all the A will be positive, minus B minus BC, and all will be the negative. So effect of A, if you do the similar cases for the B, will get this value because I have explained here. So just simplify this one. Okay. Similar way for the B also, at both are high level or low level, one high, one low, then one low, one high. So similar we can calculate for the all three, is it?
Yeah.
So effect of A will be 1 by 4n and all possible A will be the positive. A plus AB plus AC plus ABC. All other will be the negative. Similarly, for the B, or that call 1 by 4n, B plus AB plus BC plus ABC other than B, all are negative. For similar C, 1 by 4n plus C plus AC plus BC plus ABC minus 1 minus A minus B minus ABC and all. So now, so this is the all individual or the main effect. So now we have to do the what? Interaction. Is it? The two-factor interaction
Sir.
effect may compute easily a measure AB interactions and all. But if we see like it will go high, low, and then differences we can get it directly. So now AB will be ABC minus BC minus AB minus B minus and all we can get. So so ABC will come. ABC will be coming ABC minus BC minus AC plus C minus AB plus B plus C means all the individual A, B minus 1 will be the negative, remaining will be the positive. Okay. So this is how ABC will calculate. This I'll keep in the slide actually. It's a you have to calculate for the B first AB. It will go for then AC, then BC. Then we have to take the average difference between the AB interaction at the two different level of C and all. So this is how we have done. So now if you see that how the things are going, if we have the main effect, it will go A here, B this one, C this one. If we have the AB two interaction, that the cross, three possible cross can go, is it?
Yeah, yes, sir.
And if we have the ABC, will go three interactions. Now we can see the combination that all will be the at the low level. One A B A B C A C B C A B C. So this is how we have to do. So now if so this is the case for the 2 to the power 3. Now we can go for the k, that the k number of factors. So first will be the how to do A B A B C A C B C D and all. It's a 4 5. So what is the procedure? Estimate the factor effect, form the initial model. If there is a replication, the fit the full model. If there is no replication, form the model using the null probability and all. Then perform the testing, refine the model, then get the results and all. So this is the procedure in the design. So first we have to find out the factor. What is the factor we have? Then we have to whether there is any replication is there or not. If not, we have to create it. Then we can do the statistic test and all. So for K main effect, for A and B, it will go K, A, B, B, C, J, K, A, B, B, C, and all. Similar way, it will go ANOVA table and all. Is it?
Yeah, yes, sir.
Yeah. Then we'll be having a single replicate of the that design. That's I told what is the replication. Replication is something we are going to like something we are going to do the replicate or repeat and all. Then we have, if you see here, this is the example for the 2 to the power 4 design. We can see how it will work. One, that all low level A, B, A, B, C, A, C, B, C, A, B, C, D, A, D, B, D, A, B, D, C, D, A, C, D, B, C, D, A, B, C, D. So total will come. How much how much number will come? 16. We have that we have to do. If we have the replication, one replication, so 16. If we have two replication, 16 into 2, 32. If we have three that the replication, it will become 16 into 4. It will become somewhere 16 into 4 become 96. So this is how that one that we can do in the somewhere Python or the MATLAB. So what do you mean by something called blocking? So if you see the blocking, so in the case of sometime what will happen if we take many suggestion, it is that impossible to perform all the runs in a Tokyo factual. So what we have to do, whatever the homogeneous, that is something we call we have done the blocking. Like we'll be taking some homogeneous things and we'll going to block in a one like group, then we'll make different types of like in a single batch. So a single batch of raw material might not be large enough to make all the required run and all. So that's what similar way here we have one A, B, and all. So block one, block two, block three. So it become block title will become B1, B2, B3. So now it become 2 to the power 3 design. Or maybe no, two block only, or maybe the two with the three factor become. So earlier it was high, but now, so actually the blocking is to reduce the variation or factor and all. And if you see the confounding, confounding is something when we're going to mess it up. Confounding is a technique for arranging complete factorial design in a blocks. The way we are going to make the blocks, it called what you can say confounding and all. So once we'll do the confounding, we can't separate it. That is the main things. Something the technique calls information about a certain effect to be in distinguishable form or confound with the block. So in this it will like this only will be there. So confounded, we can see here how they will do block A and B, block 2 with the two runs at all in two blocks, 2 to the power 2 in a two blocks. So this is something like very basics. I will not go too much detail of this. And so similar way, it will go 1 AB, B and AB. So that's the similar way what we have done for the 2 to the power 2 design. So can we solve some problem or any doubt is there that till now? If you have, please
Solve
doubt.
some
So
problem.
yeah, that will solve that the problem. And then we'll see in the last one. So in a 2 to the power k factorial design, how many factors are studied if there is eight treatment combinations? How many? Like 2 to the power k is 8. So 2 to the power k, it become 2 into 2 into 2. 2 to the power k, 2 into 3. K will become 3. Is it? So
Yeah.
possible number of factor k will become 3. So this is the second option will be the correct option. This is how that people will do. In a factorial 2 to the power 2 factorial design, the interaction effect between the A and B defined as how we are going to define the AB average of all response? No, we can't take average now because if we take, I told you like when we're going for the interactions, so we should not have the additionality property. Additionally, it should not be there. It will be AB. It's a depends. Difference is the main effect of the A and B. A plus B, A minus B, not possible, is it?
Yeah.
So extent to which the effect of A depends on the level B. Yes, that's what it's a depending on the each other.
Okay.
So this also can't be the answer, is it?
Yes.
Just tell me in this how much degree of freedom will come for the main factor A in 2 to the power 3 factorial design of experiments. How many it will come? Number of level that we have fixed now. 2 to the power 3, but level will be the fix. Is it? Only either low and high, it become A, B, C. Three cases. One, two, three. So number of level is that we have to fix only now. For a factor A, it will be like something called. So it will become n A minus one. So it will become 3 minus 1. It's actually 2. Is it? Is it? For B, it will become B minus 1. 3 minus 1, 2. Because we have the factor is the 3. Is it?
Yeah, correct, sir.
Yeah. This is actually not correct. It become 3 minus 1 equal to. Which of the following effects can be estimated in a 2 to the power 3 factorial design? What we were having that I have shown one graph actually. Three individual effect, then A, B, C, A, B, B, C, A, C, then A, B, C. So this will be the correct answer, is it? So means 2 to the power 3 factorial design, we can calculate 3 main effect, 2 combination effect, 1, 3 factor interactions. No. So it will become one way ANOVA. Is it? Only one interactions, not possible
Yes.
because we'll having 3 2 factor, 1 3 factor, then only 2 factor at a time. No. Which of the following is not an advantage of the factorial design? Factorial design, the purpose was to study all possible combination by the definition itself. Is it?
Yes, yes.
So, ability to study interactions, yes. Efficient the use of experimental runs, yes. Required free factor, no. They can go with the many factor.
Many
Can
factors.
estimate multiple effect of, yes. So,
Yes.
actually, it's a not like factor can be, we can discuss more. So, this is not the advantage actually. Is it?
Ah, yes, sir.
In a 2 to the power k design, the total number of main effect and interaction together equals to how much it will come? Total number of main effect and interaction will become how much? So 2k minus 1, na?
Two.
Total number of treatment combination minus 1. It's a extra mean.
Yeah.
So actually this should not be,
Two.
yeah, it's a 2 to the power k. What about in a 2 to the power of 2 factorial design of experiments? The effect of factor A can be calculated. We have done, we were having A, low, high, low, high, factor B. It was A, it was this one, X, Y, Z, T. So A we can do how much? Let's say I'll go with the Y1,
Low.
Y2, Y3, Y4. Is it? So it will be
Yeah.
Y3 plus Y4 by 2 minus Y1 plus Y2 by 2. Is it?
Ah, yes, sir.
So this is the option. Confounding in a factorial design, confounding occurs when options like will be having two effect cannot be estimated properly independently. All factors are tested together. Levels of the one factors are fixed. Which one is the option?
B, sir.
Yeah, all factors are tested together.
Together.
Blocking actually to reduce the variability and all. What is the main purpose of the factorial in the experiments? To eliminate the nuisance variability, to test for the higher order interactions, to increase the what you can say replication. No. To estimate the error variance that no. To test for the higher order interactions. No, because the blocking we are trying to reduce it. Is it?
Yes.
So first option is the correct. What about 2 to the power 3 factorial experiment is blocked in a 2 block of 4 on each? What will happen?
A and 7.
So it will be,
A.
yeah, of one main effect confounded with the blocks. No, no, no. 11, what we have in a block 2 to the power k factorial design, the block effect should ideally be confounded with the higher order interactions because we have to reduce the variability, is it?
Yeah, yes.
So this is the correct option.
C.
Which of the following statement about the blocking in the factorial design is true? Which of the following statement true about the blocking in a factorial design is true? Like they are going to reduce the unexplained variability. Yes.
Yeah, variability.
So till now, I think it's done. Remaining portion that will try to figure it out. Like one more says that the session will be there. If you have any doubt, that time you can ask. Is it?
Yeah, yes, sir. Sir, this assignment questions alone, you at least a sample something you could do and send for us.
Yeah, sure, yeah, sure. I'll just send it.